next into to understand some calculation. The first is nozzle efficiency. If we look into the HS diagram here, P1, uh, point 1 and point 2 is actually the process in the nozzle, the process in the nozzle, where we don't have any work done in the nozzle, and we assume there is no heat transfer and there is no change in potential energy. All right, therefore we can see here the enthalpy at point 1 and point 0 1 and 0 2 is constant, and we see here the process from point 1 to point 2 is an expansion process. What about point 2s here? Point 2s here representing an ideal condition, where point 1 to point 2s is a centropic expansion process in the nozzle. And then P01 is the total pressure, and point 0 1 here is the stagnation point, and point 0 2 is stagnation state at nozzle exit, and P02 is the corresponding pressure at nozzle exit. So we know from this diagram that H01 is equal H02, but the pressure P01 is higher than P02. So there is pressure change during the process. From this information, we can calculate nozzle efficiency. Nozzle efficiency equal H01 minus H2 over H01 minus H2S, or equal, because H01 is equal H02, we can also write this equation using H02 minus H2 over H02 minus H2S. And we can also calculate the nozzle efficiency from the steam velocity. So V2 squared over V2S squared, or equal Cn squared. Cn is the velocity coefficient, or the ratio of V2 over V2S. Alternately, nozzle efficiency also can be expressed in terms of loss coefficient and velocity coefficient. Using this relationship, we can express nozzle efficiency in terms of loss coefficient, zeta n. Zeta n is nozzle loss coefficient, and in terms of velocity coefficient is Cn squared. Now we look into the velocity triangle. Here is the nozzle or the stator, and here is the rotor inside the turbine, or the bucket, or the blade. Okay, so we can see here the steam enter the nozzle at V1 velocity and then exit the nozzle at V2 velocity. We can see here V1 and V2 is very much different, where V2 is much higher than V1 because the nozzle speed up the steam velocity, inside the nozzle. And then if we uh, consider the rotor have um, zero friction, then V3 will be equal V2, right? And U is the rotor velocity. U is the rotor velocity. It is the same if we look at this triangle or at this triangle. Therefore, we don't have U2, U3 because it is just the same value. We can just simply use U to denote the rotor or the blade velocity. Okay, and if we look into this combined triangle, this this diagram combines these two triangles, right? So we can see U is same, and we have V2 and V3 here, and we have VU2 and VU1. Uh, the distance between from here to here is VU2, and the distance between this point to this point is VU3. From these triangles, we can have these two relationship, which is VU2 equal U plus WU2, and VU3 equal U plus WU3. Neglecting friction, W1 will be equal W2. And for equiangular system or symmetric blade, pi minus beta 2 is equal beta 3, the angle of deflection. Okay. So if you look into the HS diagram, we have looked here the HS diagram, but now we want to look in an extensive view from point 1 to point 3. Here we have from the nozzle entrance until the blade exit, until the exit of the blade. We can see here again enthalpy 0.1 equal enthalpy 0.2, pressure P0.1 P01 is not equal P02, even though it looks like equal here, but it's not equal. And we have P0 to R. R means relative. If we look into the point P0 to R to point 3S, give the relationship with the W, velocity W, or half W2 square. And the distance between P03R to point 3 give half W3 square. And the distance between 0.1 and 0.01 and 0.2 point 20 enthalpy H03. So H01 to H03, the difference will give you W for the work. And the distance between H01 to H2 will give you half V2 squared, and distance between H01 to H2S or H3SS is half V2S squared. So from this relationship, Using this relationship that we talked in the previous slide, we can calculate the work done by the blade using W equal U in bracket VU2 minus VU3, or W U WU2 minus WU3, or U multiplied by WT sine beta 2 minus W3 sine beta 3. Depend on what information we have, we can calculate the work done by blade using this equation. All right. If we have V, we can calculate using V, or if you have W, or we have a W2 or WU2, WU3, depend on information that we have. So we can use either of these equation to calculate work done on the blade. And for a triangular blade, B3, oh sorry, beta 3 equal minus B minus beta 2. And making use of the relationship W3 equal W2 over 1 plus zeta R square root of 1 plus zeta R. What is zeta R? We will talk later. And W will be equal UW work will equal UW2 in bracket 1 plus 1 over square root of 1 plus zeta R sine beta 2. Or with further substitution of W2 sine beta 2 equal V2 sine alpha 2 minus U, we can also calculate work done on the blades using this equation in terms of V2 and zeta R. Zeta R is, and we can also calculate the rotor efficiency. We have calculated the nozzle efficiency. Now the rotor efficiency H02 minus H03 over H02 minus H3S, or in terms of work and velocity, W over half V2 squared. And the total to static efficiency, is equal the nozzle efficiency multiplied by the rotor efficiency. We will get the total to static efficiency. Zeta R is the loss coefficient of the rotor.